Good afternoon. This is Professor David J. De Los Reyes, an electrical engineer by profession. Had been a professor for electrical engineering somewhere in Asia. It's in the Philippines, guys. Uh, my lesson for this afternoon will be differential equation. This is now lesson number 30 on my topic, differential equation. This is the long video form. Because actually I am done with differential calculus, integral calculus, and this is the third course, which is differential equation, and I am now on lesson number 30. Okay, let's proceed, guys. The topic for this afternoon will be a solution of a Bernoulli's equation. I think this will be my last example before I will proceed with exact differential equation. On. Okay, let's proceed, guys. The topic is Bernoulli's equation, differential equation that could be solved by using the Bernoulli's equation. My topic is with numbering DE30, meaning differential equation topic, lesson number 30, and the topic is Bernoulli's equation. I think this will now be example number 4 under Bernoulli's equation. Okay, let's proceed, guys. We are given a problem that is 2y dx plus 3x dy equal to 3 dy dx. The problem is asking for the general solution. The given differential equation is this: 2y dx plus 3x dy equal to 3 dy dx. And the problem is asking for the general solution. To bring up the solution, okay, to bring out the given equation into one of the standards under Bernoulli's, we will multiply all the terms by 1 over 2y dy. Meaning, I will try to multiply the given differential equation, okay, by 1 over 2y dy. Okay, so I will now remove this one. I expedite a little bit our solution. Okay. So the given differential equation multiplied by this, what will come out for the first term will just be simply dx over dy. Because this 2y cancel with this. Right? What remains on the bottom will be dy. So this is dx over dy. Second part, this dy cancels with this. Okay? So what will remain on the second term will be 3 over 2y times x. This is 3 over 2y times x. Right hand side. This dy cancel with this. So what will remain on the right will be 3 over 2y. This is x, right? We put it on the numerator. This is actually plus 1, right? So if we try to raise it up, this will become x raised to the minus 1. So after the multiplication of all the terms by this will be the resulting differential equation. I will try to read it, guys. Dx over dy plus 3 over 2y plus quantity dx equal to 3 over 2y times the quantity x raised to the minus 1. Why minus 1? This one, I put it up. And this is similar to the form dx over dy r of y times x equal to s of y times x to the n. There is an x to the n over here. Because without this, we could solve immediately the resulting differential equation by using a solution by using the so-called integrating factor. We are done with that. But for the meantime, our topic is Bernoulli's equation. So actually, the right-hand side is actually there is an x to the n. And if there is an x to the n, this should fall under Bernoulli's equation, case number 1. Okay? We specify the value of n on the right-hand side. The value of n is actually negative 1. Right? And for case number 1, there is a substitution z equal to x raised to 1 minus n. Okay? We now know the value of n. So to take the relation of z in terms of x, we will use this. So this z now will be equal to x raised to 1 minus open quantity minus 1. The value of n is negative 1. So I put here a quantity. Okay? Minus minus will be plus. So actually 1 plus 1 will be 2. So z is actually x squared. And if we try to compute for the value of x, raise both sides of the equation to the 1/2. Right hand side, this cancels. X now will be z to the 1/2, or that is just simply square root of z. The relation of x in terms of z is x equal to the square root of z. Why we are interested in this relation? Because we will try to bring out the equivalent of dx over here. And if we try to take the differential of both sides, dx will be dz over 2 the square root of z. Actually, you can bring out this one by using the power formula. Okay, where x is actually equal to, z to the 1/2, right? So dx will be equal to 1/2 z raised to 1/2 minus 1, that will be negative 1/2 times dz. Or if we try to simplify this, dx will be dz, 1 times this is dz, all over this is 2, right? This negative, we bring it down, this is the square root of z. So actually this one is this. Because we needed the value of x equal to and the value of dx equal to put it back to this original equation, to simplify it, so that it will come out under the solution, the integrating factor. So if we try to follow this, okay, substituting the value of x and dx, first one will be, this is 1 over dy, right? And what is dx? dx is dz over 2 the square root of z is this. Plus 3 over 2y. What is x? X is actually square root of z. This is square root of z. Right? Right hand side, this will be 3 over 2y. 1 over x. 1 over x is just equal to 1 over the square root of z. So this is 1 over the square root of z. Then try to simplify this one. I think we need to multiply all the terms by... So what will come out for the first one will just be simply dz over dy. We will eliminate this 2 square root of z. So this is to be multiplied by 2 the square root of z. All the terms. So the first term multiplied by this will vanish, right? First term will just be simply dz over dy. The second part, okay, what will come out will be 3 over y times a. The right hand side will be 3 over 2y times 1 over the square of z. Actually, z to the 1/2 and z to the 1/2 is just z. So this is a. Okay? And for the right hand side, this is square root of z, this is the one at the bottom, so actually this cancels out. So what remains on the right hand side will be just simply 3 over y. This is 2, cancel with this also. So what remains on the right will just be simply 3 over y. Okay? So after the substitution, what comes out is now a simpler differential equation, and supposed to be under Bernoulli's equation. This should fall under the solution of the differential equation, solvable by using integrating factor. And this is similar to the form dz over dy r of y times z equal to s of y. Case number 1, under the solution of a problem or differential equation, solvable by using integrating factor. The integrating factor is actually e raised to This is the part of the exponent. Okay, 3 over y. This is 3 over y times dy equal to e raised to the integral of dy over y is just natural logarithm of y. So this is 3. We bring out 3, right? Natural logarithm of y. Laws of exponent, we could place 3 inside. So it is actually e raised to the natural logarithm of y cubed. We are actually taking the antilog of this. If we are taking the antilog, this will cancel out. What will come out for the integrating factor will just be simply y cubed. Okay? We are taking the antilog on this operation, antilog. Antilog of a natural logarithm, right? So the general solution now, under case number 1 for integrating factor, it will be z times integrating factor equal to the integral of s of y, the given right hand side. Again, times integrating factor multiplied by dy. Substituting, it will be z integrating factor is y cubed equal to the integral. Right hand side is actually 3 over y times integrating factor times dy plus c. Integrating the right hand side, we bring out this one. This is 3, the integral of y cancel with this. What remains on this is just simply y squared. So it will be 3, the integral of y squared dy plus c. Power formula. So this is 3 y cubed over 3 plus c. That is z y cubed equal to y cubed plus z. To bring out the original variable, we will take the equivalent of z as a function of x. Okay? And z is actually equal to x squared. It is from this. Okay? So it will become x squared y cubed equal to y cubed plus c. Simplifying a little bit, we put this one on the left. There's a common factor y cubed times the quantity x squared minus 1 equal to c. This is now actually our general solution. That's it, guys. That's how we solve a problem under Bernoulli's equation. Okay? You try to simplify the given differential equation for it to fall under case number 1 or number 2 under Bernoulli's. Then you try to make a substitution after identifying the correct value of n. Okay? You get the relation of z in terms of x and dx in terms of z. You put it back here, what will come out will be a differential equation solvable by using integrating factor. And after identifying the value of the exponent of the integrating factor, what will come out will be y cubed. And for the general solution, since this is z, this should be z times an integrating factor equal to s of y. Again, times integrating factor times cy. And luckily, for this problem, the integral of the right hand side is just an easy y, right? The integral of y squared dy. So this is actually y cubed over 3 plus c. General solution, y cubed times the quantity x squared minus 1 plus quantity equal to c. General solution. That's it, guys. This will now be my last example under the topic Bernoulli's equation. So the next time around on my long video form under differential equation, my next topic will be exact differential equation. Good afternoon, Los Angeles. I have one thing to say for those who are interested in the study of differential equation. This is for you guys. You will learn something from it. If you are good enough for me, please like, then share, then subscribe. Good afternoon, Los Angeles.